Welcome to an Ansys tutorial on parametric analysis and optimization. Parametric analysis is the study of the influence of different geometric and physical parameters on the solution of a problem. Workbench is a very powerful tool in terms of parametric analysis and optimization. Ansys can efficiently vary the specified geometric and material property values and compute the associated results without redrawing or remeshing the structure. Ansys can also determine the correlation between specified inputs, such as geometric and material property values, and specific outputs, such as stress and deflection. In this tutorial, we're going to look at the radii of two connected double cantilever beams as shown. We will look at the correlation between the radii and the equivalent stress. We will then optimize the size of these two beams based on a specific equivalent stress and the minimization of the mass. The dimensions of the double cantilever beam are shown in this figure, where the units are given in millimeters. So the length of the beams are 30 millimeters. There's a 14 millimeter center to center distance between the two beams, and the beams have a 4 millimeter diameter. This is a relatively long and detailed tutorial, but I believe you will find it beneficial. Thanks for watching. When doing parametric analysis in Ansys Workbench, it is often easier to keep the geometry separate from the static structural analysis system. So to begin with, in this tutorial, we will create a geometric component system. So we'll open the component systems drop down. We'll come down to geometry, left click, drag it into the project schematic window, and let it go. Then we will double click on geometry to open SpaceClaim. The problem is defined in terms of millimeters, which are the default units in SpaceClaim, so I don't need to do any changing of the units. I do, however, like to change my sketch plane, so I will come over and right click, left click, select new sketch plane, hover over the XY axis and click on that. Then I'll click on plan view to look at that straight on. The first thing I will do is build my square wall, so I'll click on the square or rectangle tool. I'll come down and click on define rectangle from center. Then I'll come and click on the center and I'll drag this window out and I can type in 20 tab 20 enter and I have my rectangle built. I can now middle mouse button to scroll and rotate the structure around. I'll come up to the pool tool and click on pool. That switches me to 3D mode. I will then click on this area and the yellow arrow and drag this back, and I will stretch that back 10 millimeters. I'm now ready to draw my circular cross sections for my beams, so I'll come back up to the sketch tool, click on the sketch tool. I can see that my sketch plane is on the front face of my rectangular or square wall, which is what I would like it to be. I will click on the Z-axis to look at this straight on. I can now come up to the circle tool and click on the circle. I see that I have crosshatches on my cursor and I don't have the square to draw a circle, so I actually need to select this sketch plane. And now I can come and I have the cross hatch on my circle tool that I can use to select and build my circle. I'll come down 3 units from the top and click and drag out a 4 millimeter circle. So for enter, I can now come up to select and click on this circle and do a move with a control to copy that. So I'll click on the move tool. I'll come over and highlight the vertical arrow because that's the direction I want to move the circle. I'll hold down the control button and drag that down. I need to drag that down 14 millimeters and enter. I now have my 2 circles drawn. I can hit escape and now I can rotate this and I can see my circles. I can come up to my pool tool And I can click on these two circles. So I'll click the top circle, control click the bottom circle, and now I can pull these circles out, and I need to pull them out 30 millimeters. So I'll stretch that out and type in 30, enter. I can now build the end plate that goes on the end of these two circular beams. So I'll hit escape and escape. Then I can come back to my sketch mode by clicking there, and now I can move this sketch plane out to the end of these cantilever beams by moving it out there and clicking on them. So I now have my sketch plane out at the end of my cantilever beams, and I'm ready to start to draw the end plate. So to do that, I'll click on Plan View to look at it straight on, and I'm just going to draw the end plate graphically. I want it to be just as big as needed to contain these two cross-sectional areas of my beams. So I'll come to the rectangle tool, I'll click on this top point and drag it down and just encompass my two cantilever beams, and I'll let go. Now I can escape out of that, middle mouse button to rotate, and now I'll come up to the pull tool and I can pull this area. So I'll click on it. I also need to pull this face and this face, and then I will pull that out 5 millimeters. So 5, enter. Now you can see over here in my structure tree that I have one solid and one surface. I don't need to bring that surface into Ansys Mechanical, so I will click on the surface. I now need to create the parametric components. To do that, I come up to Select, and I can click on this beam, click on Pool, and when I have clicked on Pool, you can see that the radius shows up with a P by it. P means that that can be turned into a parameter. So I'll click on the P. I can see now that it is grayed out. If I come over here to groups, I can see that I have created a group. If I double click on this group, it's a ruler dimension of 2 millimeters, and this is a parametric group that right now consists of the radius of this top beam. I'm going to double click on group, and by double clicking on group I can change the name, and I will call this top beam radius, top beam rad. Now I need to do the same thing to the bottom beam, so I'll come down to the bottom beam, click on it, click on the P. I can see that it creates another group. I'll double click on that to open it, and then double click again and click on bottom beam radius or rad, and then click enter. I've now created the parametric components of this beam configuration. I'll do the rest of the parametric analysis in Ansys Mechanical. I can close the space claim window, and when I look at my project schematic window, I see that a parameter set has been added. I will now come up and minimize the component systems, open analysis systems, select on a static structural, drag it up over the geometry and release it, and I now have the parameter set which is connected to the static structural. You can see the parameters here, and the geometry has also come through. Now I can double click on this parameter set, and I can see that the parameters that have been set so far are my top beam radius at 0.002 meters and my bottom beam radius at 0.002. Before opening Mechanical, I see that I have a lightning bolt now on my geometry since I added the parameters. So I need to right click on geometry and click Update. Then I get the green check in the geometry, and I'm ready to open Ansys Mechanical. In Ansys Mechanical, all we need to do is a simple static solution with an end load. So I've already done that analysis to speed up this tutorial. I'll just review the process that I followed to develop that analysis. So you can see my geometry has been checked. This little hash through the check mark means that the geometry has been successfully meshed already. So I can come down and click on mesh and I can see the mesh, and I increased the resolution from the default 2 to a resolution of 6 to give myself a more refined mesh. Then I came to static structural and I introduced fixed supports, and I put fixed supports on these 4 edges. So that's the boundary conditions for my beam configuration. And then I applied an end load in the negative y direction of 200 newtons. The output that I looked at was equivalent stress, and you can see that the equivalent stress seems to make sense. As this was getting pushed down on, I would have a stress in the top and the bottom here, and also on this where this end plate tries to keep these 2 beams from rotating. Then on total deformation, this also makes sense. I have my largest deformation out on my free end. Now I'm ready to develop the parametric component of this model. So I need to select the outputs that I want in my analysis. And so the outputs that I want are equivalent stress. So I'll come to equivalent stress and click on it. And then I'll scroll down here to where it says results and the maximum. And I'll click on that empty box to get a P there, meaning that that is going to become a parametric value. The other parametric value I want is on the geometry. So I'll come up and click on the geometry, and then I will come down to properties and I will click on the mass. And so I want to minimize the mass, and so I'll make that a parametric value as well. Now I'm ready to leave Ansys Mechanical and go into Ansys, the project schematic window. Ansys Workbench uses the Design Exploration tool to do a parametric optimization. This toolbox has various ways to look at design correlation data and results. The general steps for doing a parametric optimization consist of starting with a what-if analysis. This is a best guess approach, and it can use Ansys generated data or a manually entered data to perform the analysis. We then move to the correlation studies, where we assess what actually matters to the output. We then run a set of design experiment studies where we take the parameters that actually matter and constrain them to a design space. We then look at the response surface to see how the inputs can be used to predict the outputs based on mathematical models. We then optimize to a maximum or a minimum or a specific value. A Six Sigma or robust design can then be done to make sure that the theoretical results actually will work in the real world. In the Design Exploration toolbox, the direct optimization helps us perform a what-if analysis. In this tool, you can have Ansys generate a list of cases, or you can manually type in the parameters and then have Ansys solve for each set of parameters. In this type of analysis, it's not clear how one parameter affects another. It is also not clear what parameters are really the drivers for the optimization. However, it can provide pretty good results with relatively vague inputs. The parameter correlation tool allows us to identify the parameters that affect the variables of interest and identifies the degree to which the variables are affected. A sensitivity plot shows what particular quantities are sensitive to. The response surface tool uses design of experiments methods and takes weighted inputs from the parameter correlation analysis and distributes sample points optimally within a bounded design space. A design of experiments runs a set of points similar to manual entry, but the points are determined with sophisticated algorithms. The response surface optimization interpolates between design points determined in the response surface tool and gives a smooth mathematical formulation that allows for a refined determination of the optimized parameters. The Six Sigma analysis identifies the cases that can actually be manufactured. We will now go through a tutorial explaining each one of these tools. To perform a parametric optimization in Ansys Workbench, we will first do a what-if analysis using the Direct Optimization tool. So we click on Direct Optimization, drag it to the project schematic window, and let it go. When you do that, it will open up this Direct Optimization toolbox. To begin, we will then double-click on Optimization to open up the optimization window. After opening the Direct Optimization toolbox, these are the windows that you will see. In this top corner window, we have the outline of the schematic. Down here we have the detailed specific properties of our optimization. Over here we will enter in our design constraints and objectives, and then down in here we will see various outputs. So to begin the optimization process, I first come and look at the geometry that has been brought in. So I'll click on top radius, and in top radius it says that there is a lower bound of 0.001 and an upper bound of 0.0025. Those are adequate upper and lower bounds for the radius values that I want to use for both the top and bottom radius. If I wanted to change those, I would simply click on the box and type in a new number. Then, after making sure that the bounds on my geometry are how I want them to be, I come up to Objectives and Constraints. And then we set those objectives and constraints over here in our optimization window. And I come here to the parameter, click on the drop down, and I can see the 4 parameters that I have set in my model. I'll click on the top radius and come to type, and it says no objective. I'm going to change that by clicking the drop down to minimize the top radius, and I'll enter in a target value of 0.001. The default value here is 0. Then the grayed out no constraint comes here, so I can't edit this, but that's because I've already set the constraint over here when I set my geometry. I can also see that when I set this top radius parameter to minimize it and set that objective, this minimize P1 showed up under my objectives and constraints. So now I'm ready to move to my second, and I'll look at the bottom radius, and when I click on that, I see that this P5 has popped up under my objectives and constraints. I'm going to go ahead and minimize this as well. I'll give it a target value of 0.001, and again, no constraint. I'm now ready to look at the equivalent stress maximum value, and I'm going to set this to seek a target instead of minimize it. The target that I'm going to seek is 3 e to the 8 pascals. And so now over here on no constraint, I've got a drop down window because I haven't set any constraints on the maximum equivalent stress. And I'm going to click on here to set an upper bound, and the upper bound that I'm going to set is 3 e to the 8th. Now I could also come over here and select values equal bound and set that to 3 e to the 8th, but you would have very few, if any, solution sets that met that condition. So it's typically better to use an upper or a lower bound. Then I'm going to set my last constraint on my mass, and I'm going to minimize this. I'm going to give it a target value of 0.04 kilograms, and I'm going to come over here and set a constraint of an upper bound of 0.04 kilograms. So I have now set all of my objectives and constraints, and I have checked my geometry. I'm now ready to come up and set the details of my optimization. So I'll click on Optimization. I'm going to come down here, and for method selection, instead of leaving it on auto, I'm going to click on this and then click manual. And then on the method or name, I'm not going to use the adaptive multi-objective. I'm going to click the drop down and change this to screening. I can now come down and change the number of samples and set the number of samples here to whatever I want it to be. I can give it 20 samples, for example, enter in 20, and then I can change the number of candidate samples. I'll go ahead and leave that as the default as 3. So I have now set my optimization. I've set my objectives and constraints. I have my geometry in there. In terms of parameter relationships, if I wanted to set a parameter relationship, for example, I could let the top radius, which would be P1, I can type P1 and then I can set that less than and equal to or greater than and equal to, and then type in a new expression over here, P2, for example, and then click enter, and I have set a new relationship, a parameter relationship that would then be used in the results as well. I'm not going to use any parameter relationships, so I'm going to right click on this box and then click delete to delete that relationship. I'm now ready to generate these data, and so I'll come over here and click on update, and when I click on update, it gives me the test cases that it's going to evaluate, and I can see the values that it's using for the top radius and the bottom radius, and then it will go through and crunch these values to look at the equivalent stress and the mass. I have already run this solution, and so these answers have come up. If you do this for the first time, you will have lightning bolts in these boxes where it says that the model is updating and computing. Once all the lightning bolts over here have changed to values, I know my solution is done, and I can look at this table and see the radius values that were chosen and selected, and then the associated maximum stress and mass. And I can see there's a large range in this equivalent stress. To look at these results more carefully, I can come over to candidate points, and here I told Ansys to give me the best 3 candidates, and here are the best 3 candidates according to Ansys. This X and this star help indicate the quality of the data. An X means the result is a negative or a bad result. A star means it's a good or positive result. And 2 X's means it's more bad as compared to 2 stars would be better. So if I come over here to my first candidate point, I can see that this is an X because it actually increased the radius from my original radius of 2 millimeters to 2.0125 millimeters. It also increased the radius of my bottom member. My stress is low, and it also increased my overall mass. So not a great solution with this first point. Now I come down to candidate point number 2, and this candidate point number 1 is marked as the reference. So in relation to candidate point number 1, I reduced the radius by 7.45%. In the top radius, I actually increased the bottom radius, my stress reduced, and my mass got bigger. So looking at candidate point number 3, I see that I have a 22.36% reduction in P1, a 13.6 increase in P5, my stress is a little bit higher, and my mass has been slightly reduced. None of these solutions here are great options, but that's mainly because I only looked at 20 candidate sets. But this gives me an idea of what to come and set for my own values. So I can come here and click on this box, and I'll enter in 0.0016, and then I'll click on this box and enter in 0.0023 and click enter. And now I have a lightning bolt over here, so I will come to this box and right click and then click update custom candidate point. And what it will do is it will compute the values for the equivalent stress and the mass based on these new parameters that I set. It will take some time to do that, so while it's solving, I'll click pause. So after receiving this result, I can see that my stress is getting closer to 3. I've reduced my overall mass slightly, and I could now come and reduce these values even more to come up with values even closer to a equivalent stress max of 3e to the 8th, and that would reduce my mass as well. But for this tutorial, I'll go ahead and leave these values. We can also come down here and look at trade-offs. In trade-offs, it gives us the P4, the mass on the vertical axis, and the equivalent stress on the bottom axis, and I can see where my points lie, and the feasible points are indicated by the blue squares. I can come over here and change the X and Y axes. I can click the drop down and change the X axis to the top radius, and I could change the Y axis to maximum stress, and then I could look at my points based on that plot. Then I can come up and click on samples, and this data is handy because you can click on a line and you can see the parameter sets that you have chosen and where the values fall. You can get rid of certain lines by removing the check on the input parameters and on the output parameters. We can come to sensitivities, and sensitivities is a very handy tool where it gives us our output parameters and then it lists the sensitivities. So for example, here on equivalent stress, I can see that the top radius over here, shown in red, is a little more sensitive to equivalent stress than the bottom radius. Over here on my mass, both of them have the same sensitivity. So if we had a more complicated parameter optimization, these sensitivities would provide even more insight as to what parameters are important to consider. So this gives us the process for doing a direct optimization. I hope you found it beneficial. We'll now close this window and we will come and open up a parameter correlation. So I'll left click on parameter correlation, drag it over to the project schematic window and let it go. Then the parameter correlation tool will generate a set of design points and then compute the solutions based on those design points. It will then supply us with a measure of the strength of the change of the input compared to the response of our system. The goal is to identify the parameters that have the most impact on the desired solution or optimization. After opening the parameters correlation page, we see similar windows to what we saw in the direct optimization. In the first window, we click on parameters correlation, and then we come down and set the details. The main things that you'll want to change here are possibly the correlation type. We will use the default Spearman, and the number of samples. Here I've changed the default to be from 100 to 20. You'll also want to make sure you enable the auto stop. What this does is it allows the solution to stop if a converged solution is reached before the total number of samples is reached. So for example, if I reach a converged solution in 10 samples, I'll get an automatic stop instead of continuing to iterate up to the total number of samples. And that's a very handy feature. After setting the correlation parameters, we come up and click Update, and then that will take some time for the process to run its course. We can then come to the design points, and we can see that the design points are different than the design points that were created in the direct optimization. We can also see the results associated with these input design points. The most useful tool comes in the correlation matrix. And what the correlation matrix shows us is the relationship between the inputs and the outputs. So if I look at this correlation matrix, my diagonal should all have a correlation value of 1 as it does. What that means is the top radius is directly correlated to the top radius, the bottom radius is directly correlated to itself, and so forth. It also makes sense that these off diagonals on the inputs are zeros, meaning there's no correlation between the bottom radius and the top radius because I didn't indicate that there was any correlation. Once we get down into this part of the correlation matrix, then we begin to see what components correlate well with the others. And in this case, we have the same correlations between the mass and the top radius as we do the mass and the bottom radius, and the same with the equivalent stresses. We see that the blue indicates a negative correlation, meaning that as the equivalent stress gets larger, the top radius would get smaller. In a large correlation analysis, this would be a more colorful chart, and we would be able to identify parameters that would not need to be considered further in our design of experiments. We can also see here that there is a -1 correlation between the mass and the equivalent stress, and we see this off diagonal of -1s as would also be expected. We can then look at the sensitivities. This is similar to what we saw before in the design optimization, and we can continue down through the histogram and the determination matrix. Those are somewhat useful. The correlation scatter is also very useful. It tries to fit a straight line or a quadratic, some type of a curve that we can identify over here to the data. In this case, we can see that we get a pretty good fit due to our R values, but that we have a very large scatter in our data, a large variation as well. So this is how we use the parameters correlation toolbox. We would then minimize that, and we would go to the response surface and click and drag and drop the response surface onto. I can see that my response surface window consists of two components. The first is design of experiments, or DOE, and the second is a response surface. The DOE is used to determine the relationship between the inputs and the outputs. It's a cause and effect type analysis where we try to determine the causes that give us certain effects. The response surface then builds on that design of experiments to give us a surface that we can then use to fit more accurately data parameters that will give us the response we're looking for. So I will double click on design of experiments. It brings up similar windows to what we've seen before. If I click on the design of experiments down here, it gives me the details. The only thing that you'll typically want to consider changing down here is the type. The default is central composite design. If you click the drop down, you can see that this Latin hypercube sampling design, which is also a very common method, can be chosen. And also this optimal space filling design can be chosen. After that, we can check our geometry, and if we come to our top radius, again we're doing a new analysis here, so we can enter in a lower and upper bound, and these can be different than what we entered in for the direct optimization if we want them to be. And then I enter in my inputs for the lower and upper bound on my bottom radius as well. Then after we click update, we can come down and look at the results. Sometimes results like the parameters parallel are quite confusing, so we need to come over and deselect some of the options and more carefully look at the outputs. These outputs here are the cases that we've looked at up here in the design of experiments generated candidate set. So then I can come to design points versus a parameter, and here I can change my X and Y axes to be whatever I want them to be, and I can look at the outputs on the vertical axis, and I can look at inputs down here on the horizontal axis, and I can change those plots around. So that's the design of experiments. After doing that, I come to the response surface, double click on it, and again I come to the response surface window here, and I can set the properties, and again we can use the defaults here. I can look at the input parameters and open this, and I can see that they are the same as what I entered in for my DOE. I get a min-max search, and this will give me the minimum and maximum points considered for the output parameters. I can come down and I can look at response points, and I can modify these points and move these up and down and look at various output results. I can do that down here and move these for my top radius and my bottom radius and watch how those parameters are changing. I can look at a spider plot, local sensitivity, and local sensitivity curves. So there's a vast amount of information here that can be considered to analyze the quality of your DOE. Once we have done the response surface, then I'm ready to come and do the response surface optimization. So I'll click on this, drag it over, and I'll drop it on response surface here so that it carries over the design of experiments as well as the response surface data. Now I can double click on optimization, and this is similar to the direct optimization window that we already looked at. We'll come here to click on optimization, and we can see that right now it's got an auto method. It's going to estimate the number of evaluations at 2,000, but I'll have an auto stop in there, so once things stop changing, it will automatically stop. I can see that I'm looking for 3 candidate sets. If I wanted to change this like we did before, I could come to manual, and then I could enter in the number of samples and so forth. But I'm going to go ahead and leave it on auto this time. Objectives and constraints, I need to come back and set these objectives and constraints as I did before. So I'll set my top radius and minimize that. Then I'll click my bottom radius and I'll look to minimize that. On my equivalent stress, I'm going to set seek to a target, and the target that I'm going to enter is a 3e to the 8th pascals. And I'll set a constraint here with an upper bound of 3e to the 8th. And now I'll come over here, and my last one is my mass, and I will minimize my mass. I'm going to enter in a target value of 0.03, and I'll leave that as no constraint. Up here on target values for my radius, I'm going to enter in a 0.001 and a 0.001. So I've now entered in slightly different optimization parameters than I did for the direct optimization. But again, I can see that those were built over here as I created them. So I'm now ready to run this optimization. If I come over here and click Update, it will begin that process. I can watch the progress down here. If I click on Hide Progress, it will hide this window, or Show Progress, and it shows this window as it is propagating through the design of experiments results.